Now, what was the problem in direct map cache? If you remember in direct map cache, the problem was the conflict misses. If you remember in our last lecture, what was the conflict miss? In a direct map cache, how many lines you can accommodate?
One.
Only one line. So actually, if you bring a new block, the old block needs to be replaced. But now in set to associated cache, if there is a space in the block, if there is a space within the cache set, so you can accommodate a new line. Now let's assume if we have, if microprocessor wants to access main memory block 2, it is placed here. Then microprocessor again place main memory block 26. Where it will be placed? Set 2. So main memory block 2 is placed here.
It's 26. Manual 26.
Okay. What will be its valid field?
1.
We will be 1. What will be its stack field? For 26?
3. 1 1.
1 1 0 0 0 so forth and 1 1.
Yes sir.
Okay. So memory block 26. Now if again microprocessor access memory block 50, where it will be mapped?
इसी सेट में.
इसी set में then memory block 50 and tag field will be set valid and tag field will be set. Let's assume if memory block 58, it will be placed here.
Yes.
Now if microprocessor wants to access main memory block 34, then
34. तो इनमें से एक
so it
को
is
equate
now the main memory block is the set is now
full.
So we need to evict one of the block. Why we need to evict? Because now the set is full. So when the set is full, when the set will be full? When the set will be full? When all the valid fields are 1, then the set will be filled. When the set will be empty?
All valid field.
When all valid fields are 0. So initially on the system startup, the valid field is set to 0. So now we start with the problem of a direct map set. In a direct map set, each cache set consists of a single cache line. So A is 1. So A is 1. So now in this particular example, how many sets are there? 256 sets are there. So there are 256 sets and each set consists of a single cache line. So now let's assume we have a direct map set L0, set 0 and set 0 consists of L0, a single cache line. Now how many main memory blocks can be mapped to this direct map cache set? Which blocks are mapped? MB0,
256.
then MB256. Why MB256?
256.
Because there are 256 cache lines. Then MB512 and so forth so on. Now let's assume that if microprocessor has some access sequence. So the microprocessor wants to access word 7 of main memory block 0 at time ti. After some time, at time tj, microprocessor wants to access word 3 of main memory block 0 and time tk, microprocessor wants to access word 9 of main memory block 256 and time t microprocessor wants to access word 9 of main memory block word 3, word 0 and word 3 of main memory block 256. At time ty, microprocessor wants to access word 4 of main memory block 0. Now if you look at this sequence, initially at time pi, there will be a hit in the cache or miss in the cache? Miss in the cache. What will happen?
Fish from the main.
Main memory block 0 will be moved to which set? Set 0. And now it is only a single cache line. When there is a single cache line, so it will be accommodated. Next time, if you want to access word 3 of memory block 0, miss or hit? Hit. Because now the main memory block is there. It's a hit. Next time, word 0 of memory block 256. Hit or miss? Miss. Okay. How does the cache knows that now it is not there? By looking at the tag field, not the valid bit. Valid bit is 1 in both cases. In this case, initially when its valid bit is 1. Valid bit is 1. What is the tag field now? tag field is 0. If you look at the memory block 0, so all the bits are 0, so the tag field will be 0. For this, what will be the tag field?
256.
1. Not 256. 1. Because this is mad.
G is such a
The tag will be 1. The index field will be 0. What will be the tag field? 2. So now this is the tag field. So this is the tag field. So for this the tag field will be 0. For this the tag field will be 1. For this the tag field will be 2. So in this case the tag field will be 0. So initially when it looks at the index field will determine it is set 0. The tag field will say okay, MB0, the tag will be compared with this tag. So it will be a hit or a miss. Hit. In the second time it will be a hit. So what actually? Now there are two fields. First it will look at the index field. Index field identifies the set. Then it will second look at the tag field. It will look at the tag field and the valid field. If the valid is 1, so what we can say? If valid is 1 and there is a tag match, then it's a hit. Else it's a miss. When this is a miss, bring the block. Okay, set the valid field to 1 and tag field is set according to the main memory block address. Okay, now in the second time there is a hit. Now the third time main memory block 256. So actually what is its tag field? Tag is 1 and the store tag field is 0. It's a hit or a miss? Miss. When the miss, so then what will happen? Main memory block 0 will be replaced with which?
256.
256. What will be its valid field? 1. What will be the tag field? 1. So now there is a miss. Main memory block is missed. It's also possible that this set 1 is empty. This set 2 is
Empty. All the sets are
empty.
empty.
But still it cannot go to set 1 or set 2 because the mapping function defined by direct map cache that this memory block can only be mapped to this particular set. So this is the problem of the direct map cache. Then again, will there a miss or a hit? Hit. Again, miss. Okay, now how many misses are there? 1, 2, 3 misses and how many hits? Hits are 2. So this problem is called as conflict miss. In a conflict miss, when two items are mapped to the same cache set, even for this set 1, maybe the valid field is 0. It means that now set 0 can accommodate some item. It can accommodate some item, but it cannot go here because of the mapping function. Okay, in a direct map cache, how many comparisons are needed to find a block? Only one. Why comparison? When memory block 0, it is mapped to set 0, and since there is only one cache line, so there is only one comparison is needed. Okay, now if you look at the same, if we have the same cache size, how many cache lines are there? How many cache lines? S multiplied by A, what is S?
256.
There are 256 cache lines. There are 256 cache lines. If we organize this into a two-way associative cache, if we organize this into the same set 1, it will be set 0, then set 1, then set 2, up to set 1,
128.
127. Now in this case, we are now what are doing here? So now we can have two lines L0 and
L1.
L1. Okay, which blocks will be mapped here?
MB0. MB1.
MB not 256.
128.
128. According to 128, then MB 192. MB. Yes, 256. Yes. MB 256. MB
128 करेंगे सर
256 plus 128 and so forth. Okay, so actually these blocks will be mapped. So initially, now this was for the direct map cache. This was for the direct map cache. Okay, now it's very interesting. It's very interesting. What will be its stack field? What will be its stack field? 0. What will be its stack field?
1
1. What will be its stack field?
2
Tag is equal to 2. In the previous example, the tag field was up to 56 was 1. समझ आई बात या नहीं? Because now actually in between now you have another line that is 128 is there, and in the previous example 128 was not here. Okay, so its tag field is 1. So let's assume that there is a miss in the cache. Now we have a miss. Miss in the cache. What 7 memory block 0? Memory block 0 is brought here and now put it in the cache MB0. When MB0 is here, what is its valid bit? 1. 1 is stack field. 0. Next time, second time it will be a hit. No problem. Third time it's a miss. When there is a miss, which block will be brought?
256
MB256. What will be stack field?
2
2. What's the valid?
1
1. So it's a miss. The next time it will be a hit or a miss.
hit
And the last time?
hit hit
Hit. But actually, what was the problem in the previous example? It was conflict miss. So if in a conflict miss in a direct map cache, if the items that are mapped to assets, they are accessed in a particular sequence, they will kick out each other. Now let's assume, if we have, let's assume, I already give you an example here. Now there is one chair here and there is one chair here. So I say that only the students who are sitting in this section can sit on this chair. Only the students that are sitting in this section can sit on this chair. Now if he wants to come on here and he is sitting here, if Ali Ghiyas wants to sit here, then he has to go back and Ali Ghiyas. So this is a conflict. Even if this chair is empty. Now if you look at the provincial assemblies, in a provincial assembly there can be only one prime minister. Chief minister. Okay, and only the member of that assembly can sit on that, not from the other. So there is a conflict because there is only one seat available. There is one seat available. In a direct map cache, the conflict miss arises if the blocks that are mapped to that particular set are accessed in sequence. So now we have MB0, then MB56, then MB512, and then if this is the sequence, there will always be a conflict miss. There will always be a conflict miss. Okay, now the same can be concept. So now if you look at this is how many associative cache? 2 way. If we again have to map the same problem, now we have set 0, then set 1, up to set what? Set 63. So now we have L0, L1, L2 and L3, because now there are 4 lines, the same line. Which memory block will be mapped here? 4, MB192 plus 64, MB 256, 0, 1, 2, 3, 4. So what will be the tag field? 4. So now we have mapped A is equal to 4. Okay, now if we increase A, what is the advantage?
conflict miss जो है वो
The chances of conflict misses are reduced. If we increase A, the chances of conflict misses are reduced. But if we increase A, what's the disadvantage?
length of tag जो है वो ज़्यादा हो जाएगा और
The
comparison
length of tag will be increased and the number of comparisons will be more. The number of comparison will be more. How many comparisons will be required in this case?
4
2 comparisons. How many comparisons? 4. In a direct map cache, how many comparisons?
1
1. Okay. Now what about the replacement policy? In a direct map cache, the replacement policy is very simple.
Simple. Yes, sir.
Whenever a new block is coming and if there is a miss, the old block will be kicked out. But in a two-way associative policy, then we need to decide
Which block
which
should
block
be?
to evict. Should we evict MB0 or MB256? Now all of them are full, and all of them are occupied, and there is a new block. Then we need to decide which block to evict in case of a cache miss. Now we will solve some problem. Okay, now there is direct web cache is one extreme. There is one other extreme. We call it associative cache. So we call it associative cache, fully associative cache. In a fully associative cache, S is equal to 1. S is equal to 1. So there is a single set. How many set?
एक ही set होगा.
In all the main memory blocks
Can reside on this set.
or that, and that is actually so all the blocks. So it is A0, L0 up to LA minus 1. Now, and how many comparisons? There will be a lot of comparisons. So I will now formalize it. I will now formulate it. Okay, so now let's assume L. L is the number of cache lines that can be accommodated in a cache. So what is L? L is actually equal to S multiplied by A. What is S?
Number of sets.
Number of sets. What is A?
Number of sets in line.
Associativity. It is called as associativity. The number of cache lines within the set. So the total number, it is the total number of cache lines. The total number of cache lines. So for direct web cache, cache A is equal to 1 and L is equal to S. Okay, for fully associative cache, this is one extreme. How many comparison?
Only one.
So fully associative cache, what is
A is equal to S.
S is equal to 1 because there is a single set. What is L?
It is equal to A. It is
Okay, so now how many comparisons we need? L is equal to A, we need L comparisons. Actually, if you remember the previous example, how many sets were there? Total 256. So there were 256 cache lines. What was L? 256. So in this case, L was equal to S, and now in the direct web cache, A is equal to 1, and in the full associative cache, S is equal to 1. How many comparisons we need? S comparison. Okay, so if there are 256 cache lines, there was one comparison, and S is equal to 1. How many comparisons were needed? 256 comparison. And 256 comparison means we need how many comparators? 256 comparators. And in this case, how many comparators?
one.
A single comparator. Now if we have A-way associative cache, okay, so now how many comparisons are needed? A comparisons. A comparison. And what is, how you can define A? A is equal to L divided by S. And S is actually the number of sets within a cache. Okay, now we will revisit some problems. So a memory consists of 64 kilobyte. memory consists of 64 kilobyte. The block size is 16 byte. The block size is 16 byte. The cache size is 1 kilobyte. So the problem is this: you need to partition into 3 fields. And take field. How can you partition the main memory block address? Okay, and assume that the memory is byte addressable. The memory is byte addressable. So if you look at here, so if you look at 64 kilobyte, how you can write?
2 की power
So how many bits? How many bits are there? 6.
2 is for 16 आएगा सर,
This
तो
was
byte
byte is byte address. Okay, byte. So there are 2 is for 16 bytes. So when there are 16 bytes, so actually what is the size of this main memory block address? So the main memory block address. Okay? So can we write it like this? So it is, what does this field identify? This field identify a block within a memory byte, byte within a memory block. What does this index field identify? No. A set. The set within what? And assume that we are using now the direct map cache. A set and the tag field. Okay, now if you look at this problem, now see how, why I have seen typically the cache size is larger and typically the main memory size is very large. But for the sake of simplicity and for illustration, I have assumed a very small memory block. So if you look at 64 kilobyte of memory, so now we have 64 kilobyte of memory. So can we write it like this? Byte 0, byte 1, up to byte 15. Can I write it like this?
Yes, sir.
Okay, so this byte 0 to byte 15, this constitute what? Main memory block 0. Then byte 16 up to byte 31.
MB1.
What does it represent?
MB1.
Main memory block 1. Okay, and lastly, okay, if you say it is 64 kilobyte, so the last, so what will be the first address? The first address will be 0, 0, 0, 0, 0, 0, 0. How many bits? 16 bits. If I write it in hexadecimal, so the first address will be 0, 0, 0, 0. What will be the second address? 0, 0, 0, 1. What is the byte 2? And what will be the last address?
1 1 FF. 16 will be.
Because 16 bits?
ठीक है सर.
FF of what will be the last byte? Which byte number? Byte number 65,535 because it is 64 kilobyte. So what is 2 to the power 16? So it will start from 0 to 2 to the power 16 minus 1. So 2 to the power actually 2 to the power 16 minus 1. and in general we can write it 2 to the power a minus 1. What is a? A is actually this complete block main memory address. This is a. Now main memory block 1. Now if you look at there, if you are okay, now if you look at the cache size, and it's direct map cache. It is a direct map cache. So cache, what is the size of cache? 1 kilobyte. 1 kilobyte. What is the block size? How many? What is L now? What is L now?
Line size 16 bytes.
L is the total number of lines that is in the cache. So what is L? Can we write it like this? L is equal to cache size divided by main memory block size. What is the cache size? 1 kilobyte. What is the block size?
16 bytes.
16 byte. So actually 2 to the power 10 byte divided by 2 to the power 4 byte. Byte will cancel out. It is 2 to the power 6. So how many cache lines are there? 64 cache lines are there. So if you look at the cache now, so in cache we have set 0, set 1, up to set what? 63. Which main memory block will be mapped to set 0?
MB0, MB64, MB128.
Which main memory block will be mapped here?
64.
And so forth, so on. Okay. Now, if we look at here, now if we say that now we are accessing byte number 10, we want to access byte number 10. So whenever we want to access byte number 10, so actually what will be its address? 1010000000000000. Am I right? Okay, so this is byte number 10. So the least significant bits will identify a byte within a block. How many bytes are there within a block? 4 bytes. So actually the least significant bits, 4 bits of the main memory block address will identify a particular byte within a particular block. So can we, okay, now that means, now this is actually byte number 10 of main memory block number what? 0. So the most significant is actually the main memory block number. So main memory block number. So actually this field, this is the byte, and if you look at this tag and index field combined, this is actually the main memory block number. Okay, now if you look at, if we want to access byte number 24, if you want to access byte number 24, so byte number 24 is 16 plus 8. So 1000 and 1000000000, and so all will be zeros. Okay, so this is 8 plus 16 is 64. So actually, it identifies. This is a byte inside. Of which block number is this? Okay, if you look at this byte number 24, this byte, what is byte number 24? Byte number 24 is actually belongs to which block? Memory block 1. Okay, now why I have written it in byte 16? Now it also depends on your reference. We are starting from byte 0 to byte 15. But if you look at this, actually it is byte 0. So actually, if you say it is also byte 0, byte 1 up to byte 8. So now the index starts from here. Okay? So it's the reference. So if you say, if we have the absolute reference, so it's byte 0 to byte 15, then byte 16 to byte 31, then byte 32 to so forth so on. But if the reference starts from here, so this is actually byte, the first byte of main memory block 1. Byte 1 is the second byte of the main memory block 1. So actually if you look at byte 24, it is actually byte 8 of memory block 1. So it is also for memory block it is byte 8. So this identifies the least significant bit identifies a byte within the memory block. Agree? Now if you look at this main memory block number, so the most significant will identify the main memory block number and the least significant will identify a byte within a main memory block. Now if we further divide this main memory block number, the main memory block number is further divided into the index field. And the index field identifies what? A particular set within a cache set. Within the cache. So what is index field? So the index field is actually how many bits are required for the index field? So the number of bits identified. G. What can be the formula? So yes, 6. And the remaining bits?
10.
Are 10 feet. 6 plus 4? 10. And then what is actually 16?
16.
Why it is 6 bits? Why? Can anybody? Why it is 6 bits? I can prove it. It's why it is 6 bits.
So 64 set 0
This block size is
0 to 64 set
I know that. But why it is?
2 raised to power 6.
it is a block size cache line.
64. 64.
No. It's a tag field. This 64 is this index field. Why this is tag field is